This code starts by trying to connect to Google Drive using the Google Colab library if it is being run in a Colab environment.
It then navigates to a specified location within Google Drive.
If the connection is successful, it proceeds to install the nose library.
This code snippet helps determine if it is being executed in a Colab environment. If it is running in Colab, it sets a variable called in_Colab to true and outputs, "We're running Colab." Otherwise, it sets in_Colab to false. It is commonly used to configure Google Colab for machine learning projects or activities.
This code snippet sets up the Jupyter Notebook environment to automatically reload modules when they are updated.
It then imports a module called helper and creates an instance of a class called helper from that module. This is convenient for development scenarios where module updates need to be quickly reflected in the working environment without manual reloading or notebook restarts.
This code includes commonly used libraries and modules for machine learning and deep learning tasks.
The code imports libraries like NumPy, Pandas, Matplotlib, and TensorFlow to work with data, create visual representations, and construct neural networks. This code imports modules from scikit-learn to perform various tasks for time series analysis, such as splitting data, selecting models, pre-processing data, evaluating metrics, and conducting regression analysis. This function allows for the importation of modules from TensorFlow to construct deep learning models with sequential layers such as dense, LSTM, and convolutional layers. It also brings in modules used for neural network callbacks such as early stopping and model checkpoint. The code imports modules that are used to regulate deep learning models by applying regularizers.
This code establishes a framework for conducting data analysis, preparing data, building models, and assessing them.
It utilizes a range of machine learning and deep learning techniques. This code sets up variables like !ticker, !index_ticker, and !date at !fact. The program then sets up a pathway to a specific folder location containing the data files by using these variables.
The program reads a CSV file with training data for a specific stock ticker and its corresponding index data from a designated directory.
The program reads a CSV file that contains validation data for the ticker and its corresponding index data for the index_ticker from a specific directory in the sample dataset.
This code fetches stock market data for a particular company, identified by its ticker symbol, e.g. AAPL, and its related index ticker symbol, e.g. SPY.
The data is stored in CSV files located in different directories, and it is used for both training and validation tasks. This code program compares the daily returns of Apple, AAPL's stock prices, and the S&P 500 index SPY. It calculates these returns and then displays them visually on a graph for comparison.
This code imports required libraries and sets the visualization style using SNS.set. It takes the close and AJ-close columns from the training data for Apple and the index.
It generates delayed versions of the close column for Apple stock and the market index.
It computes the daily percentage change in the prices of Apple stock and the index using the previous day's prices.
It makes a new plot with a set size for the figure.
It shows the closing prices of Apple and the index on a single graph.
The title of the plot is AAPL versus SPY, and the x-axis is labeled as time.
A legend is included on the plot to distinguish between Apple and the index.
This code gets the daily stock prices for Apple and the S&P 500 index, calculates their daily returns, and finally creates a graph showing how their prices change over time. This piece of code generates a line plot that compares the returns between Apple stock, AAPL, and the S&P 500 ETT SPY.
The plot displays how the returns of these two stocks change over time.
The x-axis shows the passage of time, while the y-axis represents the returns of the stocks.
This code creates a plot figure that is 15 inches wide and 8 inches tall.
It shows the returns of Apple, AAPL, and S&P 500 ETF SPY on the same plot with separate colors and labels. The plot is titled AAPL versus SPY returns, and the x-axis is labeled time. A legend is included to explain which line corresponds to each stock. This code generates a histogram that illustrates the distribution of returns for Apple stock data. The histogram is divided into 5,000 bins and displays returns, ranging from -10 to 10 on the x-axis. The plot size is set to 15 units wide and 8 units tall. To view the histogram, the plt show command is used.
This code generates a histogram for the returns data in the SPY's dataset.
The histogram is divided into 5,000 bins, each representing an equal interval to display the frequency of returns. The x-axis ranges from -10 to 10, showing the distribution of returns in the SPY dataset.
This code creates a plot that compares the adjusted close prices of Apple stock, AAPL, and an S&P 500 ETF SPY.
It defines the figure size, plots both assets on the same graph, sets the title to AAPL versus SPY, adjusted close, labels the x-axis as time, and adds a legend to show which line represents each asset. This code prepares financial market data for analysis by creating additional columns and performing calculations on the dataset. This is what the code does explained simply.
This process involves checking the dataset for any missing values, and removing any rows with missing values if they are found. We are creating new columns in the dataset to store the close price of the asset from previous time periods up to lag 4. This process involves calculating the percentage returns using the close prices and then saving this information in a new column.
The program computes past returns for a maximum of 5 time periods and adds these values to new columns in the dataset. The code calculates simple moving averages SMA for different time, windows 5, 30, 45, and 60 periods, based on the close prices. It then adds these calculated average values into new columns in the dataset. It adds the closing values of another asset, specifically SPY, as a new column in the dataset. The code calculates the percentage returns of the SPY asset and includes this data as a new column in the dataset. Lastly, any rows with missing values are removed from the dataset before it is returned in a preprocessed form. The code analyzes financial market data by generating delayed values, computing returns, calculating moving averages, and integrating information from a different asset to facilitate analysis. The code calls a function called preprocess and gives it 2 inputs, data_train and index_data_train.
The function processes the data in data_train using the index in index_data_train. The updated data is saved in a new variable called data2. Finally, the code displays the information inside data2. The code data2 described is a function that provides a summary of statistical information about the data stored in the data frame data2.
This includes details like the count, mean, standard deviation, minimum, maximum, and different percentiles, 25%, 50%, 75% for each column in the data frame. It offers a concise overview of the numerical data within the data frame, aiding in grasping the data's distribution and key characteristics quickly.
This code computes the correlation matrix of a dataset, indicating how closely the variables are related.
It then presents this matrix as a heat map using the Seaborn library.
The heat map graphically represents the correlations between the variables. Strong positive correlations are shown in red, strong negative correlations in blue, and no correlation in white.
Through this visualization, one can easily grasp the relationships between the various variables in the dataset. This function splits a dataset into different sections based on time series data.
I will simplify the explanation of each step for you. The function accepts a data frame called df as its input. The data is split into 5 parts, using the time series split function to perform time series cross-validation. It removes the returns column from the data frame to separate the input features x.
In this step, the code isolates the target variable, denoted as y, by choosing just the returns column from the data frame. The code iterates through the splits created by time series split, allocating training and testing datasets for both input features x and output yy in each iteration.
In the end, the function provides the final split of the data as x_train, training data, I_train, training labels x_test, testing data, and y_test, testing labels.
This function divides the data into training and testing sets, using time series cross-validation with 5 splits. This code creates a function named normalization that normalizes the data in a data frame using the standard scalar technique.
I will break down the code for you step by step to explain its function.
Set the window size to 30. To create a standard scalar object, you can use the following code. Python from sklearn. Preprocessing import standard scalar.
Scalar equals standard scalar, ..
This code imports the standard scalar class from the scikit-learn library and creates an instance of the scalar object.
Loop through each row in the data frame.
Define a window around the current observation by specifying its size with the window _size. Adjust the scaling of the values in the window to make them fit. To proceed, retrieve the current observation and apply the scalar that has been trained and fitted to transform it. Replace the current observation in the data frame with the scaled observation. Repeat this process for every entry in the dataset. Lastly, give back the updated data frame along with the trained scalar.
This code rescales each data point in a dataset by using a standard scalar that is trained on a group of nearby data points. It then adjusts each individual data point according to the trained scalar.
This code creates a function called normalization_split_train that accepts 2 data frames named df and df1. The data is processed before using the function preprocess, which takes the data frames df and df1 as inputs. The data is divided into 2 parts for training and validation using the train_test_split function. The function normalizes the training and validation features and target values separately. It uses the normalization function for this process. When data is normalized, it is scaled down to a common range. After this process, you get the normalized data and the scalar that was used to normalize it. The function ultimately provides normalized training and validation data, along with scalars for the features and target values. This code prepares the data by organizing it into training and validation sets, and standardizes its values for training and validation. It then gives back the standardized data and the tools used for standardizing for future use. This code creates a function named normalization_split_test that receives 2 data frames, df and df1 as arguments. The input data frames are prepared for further processing by applying a function called preprocess. The clean data is then saved in a variable called data_preprocessed. The code then takes the feature columns and the target column returns from the preprocessed data and saves them as x_test_processed and y_test_processed. To prepare the data for analysis, the feature data x_test_processed and target data y_test_ Processed are normalized using a normalization function.
This process results in two outputs for both feature and target data: the normalized data itself, and a scalar value scalar_x_test, for features, and scalar_y_test, for targets.
These scalars allow for the data to be transformed back to its original scale if needed. The function ultimately outputs the normalized feature data, normalized target data, as well as the scalars for both the features and target data. This function takes input data frames, separates the features and target, normalizes the data, and then returns the normalized data along with scalars that can be used to transform the data back to its original scale. This code creates a function named plot, which requires two inputs, y_validate_processed, and predicted_stock_price.
In the function, a new plot is generated with dimensions of 15 units in width and 10 units in height.
It shows the real stock returns from the processed y_validate data in red with a label actual returns. The graph shows the expected stock returns based on the predicted stock prices in blue, and it includes a label predicted returns. The title for the plot is Apple Stock Price Predictor. The x-axis is labeled as time, and the y-axis is labeled as Apple stock price. A legend is included in the plot to help differentiate between the actual and predicted returns. The function is used to create a graph that shows the real and predicted stock returns for Apple stock prices, allowing for a comparison between them. This code calls the function normalization_split_train with two arguments: data_train and index_data_train. This function is expected to normalize the data in data_train and then divide it into training and validation sets.
The function will provide the normalized and split datasets for training and validation: x_train_processed, y_train_processed, x_validate_processed, y_processed. It will also return the scalars used for normalization: scalar____y_train, scalar____evil, scalar__evil.
This code snippet readies the data for training by standardizing it and dividing it into training and validation sets. It also provides the scalars that were utilized for standardization. This code prepares a test dataset by normalizing its features and target values.
It then splits these normalized values and the corresponding normalization scalars into four variables: x_test_processed_processed_processed_target, scalar_x_test, scalar___y_test.
First, the code imports required libraries and generates a random regression dataset using the make_regression function. Then, it creates a random forest regressor model, trains it on the dataset, and calculates the importance of each feature by accessing the feature_importances_attribute of the trained model.
Afterwards, the code assigns the feature names to a variable, and then goes through each feature to display its name and importance score.
The final step involves visualizing these feature importances through a bar plot created using matplotlib.
This code creates a random forest regression model from a dataset.
Then, it visualizes the importance of each feature in making predictions using a bar graph. This code employs the mutual information regression method to determine the significance of individual features and predicting the target variable.
The process begins by calculating the mutual information scores between the features in dataset X and the target variable Y. After removing the target variable column, the program retrieves the names of the features from the training data.
Afterwards, the program displays the names of the features along with their respective mutual information scores. Lastly, a bar plot is shown, displaying the mutual information scores for each feature.
This code calculates the importance of each feature in predicting a target variable by measuring the mutual information between them.
It then displays this information using a bar plot. This code defines a neural network model using the Keras library, which is a deep learning API built on top of TensorFlow.
The model includes several long short-term memory LSTM layers with dropout regularization to avoid overfitting.
Here is a simple explanation of the code. A variable named model0 is set to have no value at the beginning.
A variable named units is assigned the value of 300.
The regularization methods L1 and L2 are brought in from the Keras library. In Keras, a sequential model is created and stored in a variable called model0.
In a model, you can add LSTM layers with a specified number of units or neurons in each layer.
By setting return_sequences equals true, you configure these LSTM layers to output sequences of values rather than just single values. To prevent overfitting, dropout layers with a dropout rate of 0.2 are included after each LSTM layer. A dense layer with just one unit has been included as the output layer. The model summary provides a breakdown of the neural network's structure, detailing the parameter count in each layer and the total trainable parameters in the network.
This code uses LSTM layers to train a neural network model.
The model utilizes the mean squared error as the loss function and the atom optimizer.
2 callbacks are implemented in this setup.
The early stopping callback helps to prevent overfitting by stopping training when the model's performance on a validation dataset starts to degrade. The modeled checkpoint callback saves the best model during training based on a chosen metric, ensuring that the best version of the model is available even if training is interrupted. The model is built using a specified optimizer, loss function, and evaluation metric. The model is trained using the given training and validation data for 200 rounds, with each round processing 32 data points at a time. After training, the model displays graphs that show the training loss and validation loss across the training epochs. This helps to easily assess the model's performance during training. This code utilizes a trained LSTM model to forecast stock prices. It forecasts stock prices for both the training dataset X_train_processed and the validation dataset X_validate_processed. The predicted stock prices are stored in the variables predicted_stock_price_LSTM_train and predicted_stock_price_LSTM_val correspondingly. This code applies a trained model, model0, which is an LSTM model to predict stock prices based on a test dataset named X_test_processed. The predicted stock prices are saved in the variable predicted_stock_price_LSTM_test. This code reverses the scaling transformation applied to target variables to make them easier to interpret in their original units. The original variables were scaled using scalars named scalar_ytrain, scalar_yval, and scalar_ytest.
By using the inverse_transform method of these scalars, the processed target variables and predicted stock prices are converted back to their original values.
This process is useful for evaluating model performance and understanding the actual prediction values.
The purpose of this code is to store a machine learning model and its training history on a computer. The saveModel function is used to save the model under a specified name, while the saveHistory function is used to store the training history of the model with the same name.
This facilitates easy retrieval and reuse of the trained model and its training progress for future use. This code generates a graph that displays the actual and predicted stock returns for Apple stock. It sets the figure size to 15 by 10 units and plots the actual returns in red and the predicted returns in blue on the same graph. The plot is titled Apple Stock Price Predictor, with the x-axis labeled as time and the y-axis labeled as Apple stock price.
Additionally, a legend is included to distinguish between the actual and predicted returns on the plot. The code generates a visual comparison between the observed and predicted returns of Apple stock prices using a machine learning model.
It sets the figure size and displays the actual returns in red and the predicted returns in blue. Additionally, it adds a title to the plot, Apple Stock Price Predictor, labels the x-axis as time, the y-axis as Apple stock price, and includes a legend to distinguish between the two lines on the plot. This code calculates and shows different error measurements to assess how well a machine learning model is performing on validation data.
Mean squared error, MSE, is a way to calculate the average of how much the predicted values differ from the actual values. It does this by squaring the difference between each prediction and actual value, and then finding the average of those squared differences.
The root mean squared error, RMSE, is calculated as the square root of the mean squared error, MSE. It is used to measure the magnitude of error in a model's predictions. Mean absolute error, MA, is a metric used to evaluate the accuracy of a predictive model. It is calculated by finding the average of the absolute differences between the actual values and the predicted values. The R-squared R2 score is a statistic that shows how much of the variability in the dependent variable can be explained by the independent variables in a regression analysis. Mean absolute percentage error, MAPE, is a metric used to measure the percentage of error in predictions compared to the actual values.
The code calculates various metrics to evaluate the model's performance in predicting the target variable on validation data.
It displays the values of these metrics in the console for analysis and comparison purposes.
This code calculates metrics to assess how well a machine learning model is performing in predicting stock prices. Mean squared error, MSE, calculates the average of the squared differences between the real and predicted values.
Root mean squared error, RMSE, is simply the square root of mean squared error of mean squared error, MSE, and helps to understand the dispersion of errors in a dataset. The mean absolute error, MA, measures the average difference between actual and predicted values. The R-squared R2 score measures how well the independent variables explain the dependent variable, providing insight into the goodness of fit of the model. The mean absolute percentage error, MAPE, is a measure that shows the average percentage difference between actual values and predicted values.
The code computes metrics like MSE, RMSE, MA, R2, and MAPE, using both actual and predicted stock prices. These metrics are valuable in evaluating the accuracy and performance of the prediction model.
This code compares the actual stock prices with predicted stock prices using a model. It then creates a histogram of the differences between these values, called residuals. By showing the frequency of these residuals, the histogram helps evaluate the model's accuracy in predicting stock prices. This code generates a scatter plot to show the connection between the forecasted stock prices from an LSTM model and the differences between the real and predicted values. The x-axis displays the forecasted stock prices. The y-axis shows the differences, and each point signifies a forecasted value and its corresponding error. This visualization aids in identifying any trends or relationships between the forecasted values and the errors. The code establishes a neural network model through TensorFlow's Keras API. The model follows a sequential structure and comprises multiple dense, fully connected layers interspersed with dropout layers. In total, the model consists of 6 dense layers, each featuring 300 units and utilizing the ReLU activation function. Dropout layers are included to counter overfitting by randomly deactivating a portion of input units during training. The model is compiled using the linear activation function for the output layer, and then the model summary is displayed.
This code utilizes a neural network structure known as AND to train a model.
The training data and their labels are pre-processed beforehand.
The model is configured with the mean_squared_error loss function and the atom optimizer.
It incorporates early stopping and model checkpoint callbacks to avoid overfitting and preserve the best model achieved throughout the training process. During training, the code keeps track of and saves the loss values for both training and validation datasets to show visually.
This training progress information is stored in a variable named history1.
A plot is made to display the training and validation loss values during training.
This helps to see how well the model is performing and whether it may be overfitting or underfitting.
This code utilizes a trained neural network model to forecast stock prices. By inputting processed data for training and validation sets, the model predicts stock prices for both datasets. The resulting forecasted stock prices are stored in the variables predicted_stock_price_n_train set and predicted_stock_price_n_val for the validation set. This code utilizes an artificial neural network model named Model 1 Foot to predict stock prices based on a provided dataset named x_test_processed. The predicted stock prices are then saved in a variable named predicted_stock_price_n_test.
This code saves a machine learning model Model 1 and its training history History1 using a helper function. The model is saved with a specific name model_name1 for later use.
This enables easy access to the model and its training history without having to train it again. In this code snippet, the data is scaled using scalar objects before training a neural network.
After training, the inverse_transform function is applied to reverse the scaling process, returning the data to its original scale. The code reverses the scaling applied to the target variables y_train_processed, y_validate_processed, y_test_test, and the predicted values from the neural network, predicted_stock_predicted_train.
This code is changing the scaled data back to its original form. This allows for comparison and analysis in the original scale. The code generates a graph comparing the real Apple stock returns with predicted returns using an artificial neural network model. The plot displays 2 lines, red for actual returns and blue for predicted returns. Time is on the x-axis and Apple's stock price is on the y-axis. This visual helps assess the accuracy of the AND model's predictions using the validation dataset.
This code generates a graph displaying the real and predicted returns of Apple stock prices using a test dataset.
The plot will show actual returns in red and predicted returns in blue.
The title of the plot will be Apple Stock Price Predictor, Test Dataset with time on the x-axis and Apple stock prices on the y-axis.
The plot will have a size of 15 by 10 units. This code calculates and displays different error metrics for a machine learning model's predictions. It compares the predicted values stored as predicted stock price an val to the actual values stored as y validate processed and from the validation set. The metrics include mean squared error. MSE is a metric that calculates the average of the squared differences between predicted values and actual values. Root mean squared error, RMSE, is the square root of mean squared error, MSE. It measures the error between predicted and actual values in the same units as the target variable. Mean absolute error, MEA, is calculated by finding the average of the absolute differences between predicted and actual values. The R-squared R2 score measures how much of the change in the dependent variable can be explained by the independent variable. The mean absolute percentage error MAPE is calculated by finding the average of the percentage differences between predicted and actual values. Once the metrics are calculated, the code displays each metric paired with its value. This process aids in assessing the machine learning model's performance, specifically how accurately it predicts the target variable in comparison to the actual values found in the validation set.
This code calculates various metrics used to assess how well a machine learning model can predict stock prices.
Mean squared error, MSE, is a metric used to calculate the average of the squares of errors in a prediction model. It helps to quantify the difference between the predicted values and the actual values.
Root mean squared error, RMSE, is a method used to measure the average error between predicted and actual values.
It is derived from mean squared error, MSE, but is presented in a more understandable way in the same units as the target variable. Mean absolute error, MEA, is a method that computes the average difference between the predicted values and the actual values without considering the direction of the errors. The R-squared R2 score measures the goodness of fit of a model by comparing it to a basic model that predicts the average of the target variable.
Mean absolute percentage error, MAPE, measures the average percentage difference between predicted and actual values.
At the end, these metrics are shown to give an idea of how accurately the model predicts stock prices. This code finds the differences between predicted and actual stock prices to calculate residuals.
These residuals are then visualized in a histogram that shows how frequently different residual values occur.
The x-axis displays the residuals, the y-axis indicates their frequency, and the plot is titled Histogram of Residuals. The code then shows the histogram. This code generates a scatter plot displaying the predicted stock prices on the x-axis using an artificial neural network and the residuals, the differences between actual and predicted stock prices on the y-axis.
The plot is a visual tool to assess how accurately the AN model predicts stock prices by illustrating the spread of residuals in relation to the predicted values. This code creates a neural network model that utilizes Conv1D layers to analyze one-dimensional data like time series or signals.
In this line, Model 2 is being set up as a sequential model using Keras. To extract features from the input data, two Con1D layers are added with 64 filters each and a kernel size of 3. The rectified linear unit ReLU activation function is applied after each convolutional layer. The input shape is set using x_train_processed shape1it, which is assumed to be the length of the input data. Padding is utilized to preserve the input size during the convolution operations. The data is downsampled using an average pooling 1D layer, and a dropout layer is added for regularization. Two additional Con1D layers are included in the network, each containing 128 filters. These layers are followed by average pooling and dropout layers to enhance the model's performance. Next, the model is flattened in order to be processed through a dense layer with a single unit and linear activation function. This setup allows for the model to generate a continuous prediction. The model summary displays the structure of the model, revealing the count of parameters in each layer.
This code creates a deep learning model for analyzing one-dimensional data.
It uses convolutional neural network layers to identify important characteristics in the data and make predictions of continuous values.
This code trains a deep learning model with a convolutional neural network (CNN) structure. It defines the model's name, loss function, mean squared error, optimizer, atom, and incorporates callbacks for early stopping and checkpointing the model.
The code sets up a neural network model to be trained using the atom optimizer and mean squared error loss function. It then proceeds to train the model with the training data and assesses its performance with the validation data.
To avoid overfitting, the code includes early stopping and saves the best model, which is determined by mean squared error on the validation set, using a model checkpoint.
Once the training is done, the code utilizes matplotlib to create a visual representation of the model's performance by plotting the training and validation loss over different epochs. This code uses a convolutional neural network (CNN) model to predict stock prices. It trains the model using the training dataset and validates it using the validation dataset. The trained model, Model 1, is then used to predict stock prices based on processed input data x_train_processed and x_validate_processed. The predicted stock prices are stored in variables predicted_stock_price_CNN_train and predicted_stock_price_val for the training and validation datasets respectively. The code applies a trained convolutional neural network (CNN) model to forecast stock prices using pre-processed input data x_test_processed.
The model processes the input data to produce predictions of stock prices. This code saves a machine learning model and its training history to separate files.
The "save model" function saves the model as model 2 feet with a specified name, model_name, 2 feet to a file, while the "save history" function saves the training history as history 2 feet of the model under the same name, model_name, 2 feet to a file. This method enables storing and retrieving both the model and its training history for future use, such as evaluation or deployment.
This code reverses the scaling of values to obtain the original data. It utilizes the inverse_transform method of the scaler to convert scaled target data y_train_processed, y_validate_test, and y_test back to their original values.
The process is then repeated for predicted stock prices from a convolutional neural network CNN model. The scaled predicted prices are transformed back to their original scale using the respective scaler used during training, validation, and testing.
This allows for a direct comparison between the predicted and original values. This code generates a plot, illustrating actual and predicted stock returns for Apple stock. The plot displays actual returns in red and predicted returns in blue, with time on the x-axis and Apple stock price on the y-axis. The plot is titled Apple Stock Price Predictor. This code generates a graph comparing Apple's real stock returns with those predicted by a convolutional neural network (CNN) model. The plot displays two lines, one in red for the actual returns, and the other in blue for the predicted returns, spanning over time on the x-axis and Apple's stock price on the y-axis. The plot is titled Apple Stock Price Predictor.
This code is used to determine how well a machine learning model is predicting stock prices by calculating different evaluation metrics. These metrics help assess the performance of the model.
Mean squared error (MSE) calculates the average of the squared differences between the actual and predicted values.
The root mean squared error (RMSE) is a way to measure the error in a model.
It is calculated as the square root of the mean squared error (MSE) and provides a clearer sense of the error in the same units as the target variable.
The mean absolute error (MA) calculates the average of the absolute differences between the predicted values and the actual values.
The R-squared R2 score is a measure that shows how much of the variability in the output can be explained by the input variables.
The mean absolute percentage error (MAPE) measure computes the average percentage difference between the actual and predicted values.
These metrics are used to assess the model's accuracy in predicting stock prices.
Lower values represent better performance. The code displays the values of each metric for analysis.
This code computes various error metrics to assess how well a model predicts stock prices.
Mean squared error, or MSE, is calculated by finding the average of the squared differences between the actual values and the predicted values. Mean absolute error, or MA, is simply the average of the absolute differences between the actual values and the predicted values. The root mean squared error (MSE) is a measurement used in statistics to represent the square root of the mean squared error (MSE). RMSE is preferred as it provides a more understandable representation compared to MSE.
The R-squared score shows how much of the variability in the dependent variable can be understood or explained by the independent variables.
The mean absolute percentage error (MAPE) calculates the average percentage difference between actual values and predicted values. The code evaluates the model's performance in predicting stock prices by comparing predicted and actual stock prices using testing data. It then calculates and displays metrics to gauge the accuracy of the model's predictions. This code compares the actual target values to the predicted values from a machine learning model to calculate the residuals.
The residuals represent the errors in the predictions. By generating a histogram of these residuals, we can visually assess the spread of errors and evaluate how well the model is performing overall. This code makes a scatter plot comparing predicted stock prices from a convolutional neural network (CNN) model with the residuals, the differences between actual and predicted values.
Each point on the plot shows a pair of predicted value and residual. The x-axis displays predicted stock prices, the y-axis shows the residuals. This visual helps assess the CNN model's accuracy in predicting stock prices. This code loads a machine learning model using a function called loadModel from a helper module or file. It passes the variable model_name2 to the function. The function is in charge of loading and setting up the machine learning model that is saved with the name provided in model_name2. This code creates functions to save and load a deep learning model with TensorFlow. The saveModel function saves a model in a specified directory. It creates a new directory if one doesn't exist, and saves the model configuration in a JSON file config. And the model weights in an HDF55 weights H5. If the directory already exists, existing files will be overwritten. The function loadModel retrieves a saved model, including its configuration and weights, from the specified directory specified by model_path. It reconstructs the model using the saved configuration and loads the saved weights, finally returning the model for use.
The myModel function performs the following steps. 1. Loading a model using loadModel function.
2. Processing test data from two directories named test_dir and test_dir1.
3.
Making predictions using the loaded model. 4. Inversely transforming the predictions and actual values back to the original scale. 5. Plotting the actual values against the predicted values. The next step in the code involves loading a model for testing and saving it with the saveModel function.
Make sure to replace the model_loaded variable with the model object that you want to save. This code helps you store and retrieve a machine learning model in TensorFlow. It also lets you predict outcomes on test data and display the results visually.
In this code, two file paths are created, holdout_dir and holdout_dir1. Holdout_dir points to a file named AAPL.csv inside the sample folder in the data directory. Holdout_dir1 points to a file named spy.csv in the same directory structure. The OS path join function is used to concatenate the directory paths accurately. The code snippet executes a function called myModel by providing it with file paths holdout_dir, holdout_dir1, and a variable model_path.
These file paths are expected to be used inside the function to load data or models.
The function likely generates predictions and identifies using the data from the specified files.
This code shows the message done on the screen.